This is lecture 10 for chapter 1 for ODE, and the subject here is modeling. Now there really are two types of modeling. In other words, the word modeling is used in two situations. In one situation, the social situations, assumptions are made about a social situation based on usually on some kind of observations or ideas. After that, mathematical functions are fitted to those assumptions. Now, if the mathematics is correct, usually the mathematics is correct, then the validity of the model rests on the assumptions. Now, if you're going to use the model or use the mathematics to predict the future, there is a big question. Not only do you have to wonder if your assumptions were correct initially, you also have to wonder whether the assumptions are holding in the future or not. And there are no checks on that. The mathematics will proceed as it does, no matter what the assumptions are doing. There's another question if you use a computer program to solve the equations that you have fitted to your assumptions, because computer programming and numerical methods need to be considered from an expert standpoint to whether the method of solution is valid and what are the errors associated with that solution and whether the computer program itself is even valid. So that's one kind of modeling. The second kind of modeling is in physics and engineering, in the world of work, so to speak. It is based on the laws of physics and mathematics and is constrained not to violate them. But then there is a description of either the device or the material that's being studied. For example, if you're studying a material and it's being used in a you could say typical laboratory situation, you might use a continuum model for the material. If you're studying it in a fusion reactor, you might be looking at a quantum model for the material. Right? Also, if you have a device, you might study the device in one way if you're looking at some section of it. In another section of it, you might study a different way. An example would be some sort of electrical device. Maybe a lot of the device could be modeled in a lumped element circuit model with fixed inductance and resistance and capacitance. But if along that model you have some sharp corners that are subject to arcing, you would study those separately using Maxwell's equation in a finite element code. So we're looking here at modeling the material or the device based on what's going on with it. So this is a little bit different. There are assumptions being made, but there's more constraints because laws of physics are still not to be violated. Then the question is, why is modeling studied in a course on differential equations? And the reason is usually you're looking at the time rate of change of something. How are things going to change? How can I predict the future? And that involves variations or rates of change, and that's why you usually end up with differential equations in modeling, but not always. I want to talk a little bit more about assumptions, and we'll look at what's called a Malthusian catastrophe that always gets brought up. It was developed in the 1700s by Thomas Malthus, and it was based on his observations that at the time the population increases exponentially, but that agricultural output from land increases arithmetically. Those were his observations at that time. Now those are the assumptions. The mathematics is put to that is, of course, an exponent for the population and a polynomial for agriculture. Now it is mathematically true that any exponent will eventually overtake any polynomial. I'm going to sort of draw that situation here. So this is the time axis. So here's time, and I'll draw one curve here for agricultural output. Well, just let it be a straight line. Okay. So here's our agriculture. Of course, it could be a different polynomial, but let's say it looks like that. And here's our population. So say our population starts down here so that we have more agriculture than we can produce, than we can need. But here is that exponential, poorly drawn, of course, increasing. So this is population. This is agriculture. And here's where they cross, which they will mathematically. Eventually they cross, and this is the point of the Malthusian catastrophe. After that, of course, there's starvation, famine, widespread disease, and of course population has to take a nosedive, and then we can start up again. So that's a Malthusian catastrophe. Now the question is, are those assumptions valid? Population in most places of the world is no longer increasing exponentially. In fact, it's negative in some places. This is just quite a few places in Europe. So now you no longer have an increase in population. It's not even increasing, let alone exponentially. And as far as land, you no longer have land. Land is not needed anymore to grow crops. You can grow them in towers hydroponically. Also, there were achievements in the 1950s in agricultural output, so that agricultural output increased exponentially. So the world is now very different, because people still like to bring this up, and that leads to another problem. But I just want to point out that you have your assumptions on one hand, your mathematics on the other in this modeling. Well, I made this comment in the written lecture for the Malthusian catastrophe. Using Thomas Malthus's model to predict population agriculture would be like taking a circuit equation and expecting that it would produce it would give you the output for a device while the device is being heated. So really you're using some mathematics on a changing situation, and the change hasn't been incorporated into the mathematics. Okay, there's also an emotional attachment to the outcome or the assumptions, and I'll call this a strange narcissism. It's like, well, I think or I feel it should be that way, therefore it should be that way. And what can I say? That's a strange narcissism, narcissism based on your feelings. So one should always watch out for that when doing science or mathematics. There's some rules of thumb and some style points that go with modeling that we can talk about. One is Occam's razor. This is a very old principle. Basically it says keep it simple, or less is more. You might think if you're making a model of something that the more assumptions and the more detail you put into it, the more accurate it would be, and the idea is that's not true. Every assumption brings with it its own set of errors. If you say typically you might say the peak, we'll discuss this in a minute, a peak happens halfway through a process. Well, okay, that's the easiest thing you could say, but you might say, well, it happens at a third of the way. Well, why not 0.2? Why not 0.4? You see, all these assumptions just bring more errors and more uncertainty with them. So the fewer assumptions, that's better. Also, there's normalization. This makes things easier. Some normalization means to set some quantities equal to 1. Now, if you have the max and the min of a certain quantity, such as the amount, then it's good to set that equal to 1 for all of it and 0 for nothing. And then you can multiply later by some value and then apply your output to different situations. But some things should never be normalized. Never set time constants to 1. If you set them to 1 and they disappear out of your equation, you've lost very important information. Also, don't set any fraction with terms of different units to 1, because then you basically have wrecked all your units and you've got a problem. You can group constants together. In a later lecture there will be something that looks like this. All constants multiplied together in differential equation, you can just set that equal to alpha and throw it on the other side, and then you can evaluate it later when you're done. So this is a good thing to do. there's no problem with that. But don't set it equal to 1 and lose it. And then, of course, always solve your equations with the parameters and later evaluate. So now I'm going to go through the Hubbert model or sometimes called Hubbert Peak Model. It was developed and presented in a paper in 1956 by M. King Hubbert, and it was he used it his model to investigate the production of coal, oil, natural gas, and uranium. Now, many people talk about this model a lot, and they write papers on it, and it's obvious from what they say that they never read the original paper or never understood it. So in this class I have given you the opportunity to read the original paper, and that's on Blackboard, and also another paper in which someone made a reasonable extension of this model, and we're going to do something similar here. So I suggest you read this. If you're going into petroleum at all, you should read this, and then it will give you, if nothing else, bragging rights to say, well, did you look at the original paper? These people throw around logistics function, they throw around all kinds of terms that were never even in the original paper. So let's examine it. Also, we'll look at this model because it's really a great model, and it follows all the basic principles of modeling that we discussed so far. So the first thing in the model is to go through the assumptions. So here basically are the assumptions. You can get them out of his paper. The first is that the Earth is no longer making petroleum at an appreciable rate, so that current oil reserves can be taken as finite. Okay, that's an assumption. Is it true or false? We don't know. It seems reasonably true. Maybe in the future that will be discovered that that's wrong, but this is what the model is based on. Second, it says the majority of oil reserves are known. There might be things that are going to be discovered later. For example, with better seismic techniques that look under sand, we now have a better look at some of the oil reserves in Brazil, off the coast of Brazil, and that can happen. But he's saying the majority of oil reserves are known. He's thinking that the ones that are found in the future are not going to be appreciable size. Third, it's known that oil has been produced for years, but since about 1860 the rate of production has increased dramatically, and that is with the advent of drilling. Prior to that, oil seeps were collected, so there was some production before that, and you can see that in the model. The fourth is that at some time in the future all or most all oil will have been produced and the reserves will be depleted. Okay, and that has to do with being finite. 5, some reserves are difficult to extract. These will be extracted last, and their production will be very slow. In other words, don't expect any great big change here, and that kind of goes with number 6. Future discoveries, future improvements in secondary recovery techniques will not have a dramatic impact on the depletion of reserves. So here we have a list of assumptions, and it's possible they're not valid anymore. But right now we're going to take them as valid and proceed with the model. A little bit at terminology here. In fact, this is a test question. So he is going to use two functions. One is Q of t, which is the amount that's produced, quantity produced. And then the rate of change is the rate of production. You can fit some units to it if you want here. Barrels and barrels per year. So how are these two related? Well, if you have this function, then you take its derivative. So to get to rate of production, if you know the rate of production and you want the amount produced, then you integrate. So they're related by calculus. And we'll look now at what Hubbert did with these ideas. Okay, so what he did with them is draw a curve. He drew the simplest curve that he could draw to fit his assumptions. He made it symmetric, just as simple as you can get, while he shifted to one side or the other, and he made this typical old bell-shaped curve. Now by doing the bell-shaped curve, he has two tails. One tail to the left can be for production prior to, say, 1860 or whatever time you select for your particular reserve that you're discussing, and the other tail can be modified for future improvements in secondary oil recovery, and so here you have two tails for it, and it's symmetric, and all he did was draw the curve. He did not fit functions to it. He fit no mathematics to it. This is all he did. And like I said in the written lectures, this is just a sign of his genius. No more assumptions were added to this model than could be supported by what he assumed in the first place. And because of its simplicity, and because he didn't put a lot more bells and whistles on it, this is why his model has lasted the test of time and is still being used and quoted in different areas. So again, we have the ultimate in simplicity. We have reasonable assumptions based on data, the ultimate in simplicity. As far as the mathematics that he used, the textbook cites the memoirs of one of his colleagues, and if you read that book, you'll see the colleague who says he frequently went to coffee with Hubbert never got out of him any mathematics that he used. Never got out of him any function or any formula that he used. He didn't tell him, probably because he didn't use one. And this is a picture, a graph from that 1956 paper that's on Blackboard. This is what he drew. It doesn't even really look like a bell-shaped curve, doesn't look like a Gaussian distribution. It's just a symmetric curve. It has tails out here, okay, that you could sort of play with. You can raise this tail up here for secondary recovery. It has symmetry, and what he's drawn here is the rate of production curve. If you take the integral of it here, you will get the amount produced, and the integral of this looks something like, I'll try to draw it. Okay, so it's going to come along here, it's going to increase, and it will have an inflection point. There'll be an inflection point right at the peak. So this would be the amount. And at some point it's going to hit 1, and that will be produced all of the reserve in that particular location. So this is basically what he did, and this shows what a good model for sort of a social situation is like. He presented the most simple, straightforward model, made use of it in a reasonable manner from clearly stated assumptions based on data, didn't dress it up, didn't add unnecessary details. We are going to proceed and add some unnecessary details, but everything we do from this point on is just more or less plain. The real model happened up to this point. So now we'll look at some functions that we could fit to his model. And the two most common ones are the Gaussian function and the logistics function. The Gaussian function, as you're familiar with the Gaussian distribution, will give you the rate of production. This is already scaled here. The mean here will be pretty bad drawing. It's going to be right here, so that's your peak at your rate of production. It will also be the inflection point when you take the integral. Here's the integral to give you the amount produced. So this is the amount, and this is the rate. And by using the Gaussian function, you get a curve for the rate, which is what he showed in his paper. The other choice is the logistics function. This is an unscaled version of the logistics function. I'll show you how I'm going to scale it in a minute. So the logistics function gives the amount, and you have to take the derivative to get the rate. It looks similar, right? But here's the amount right here, and this looks like a Gaussian distribution, but it's the error function, and this is the rate of production. and this is the amount produced in red. Now what we have to do to make use of this is we have to move this peak and inflection point. Actually, we'll be working with this curve, so we move this inflection point over to where we think the peak of production and the inflection point on the amount is. So we have to move this over, and we have to figure out some other starting point, something to do with a starting point. Now here's a scaled version of it, sort of like a scaled version of the Gaussian distribution. And I've added two more parameters, the scaling factor and also some time to maximum production. I want to just show you here what this scaling is going to do. Alright, if I have the Gaussian distribution, if I have that Gaussian distribution, then if the standard deviation changes, I could end up with something that has a bigger peak or something that's flatter. So, well, that was pretty bad. Again, I've said it before, I have absolutely no artistic ability at all. None. Okay, so I'm able to change this rate of production curve by using standard deviation if I use the Gaussian. Since I'm going to use the logistics function, I'm going to change the slope of the curve Q of t by modifying that parameter b. Now if you had quite a few data points, you could throw all this on the computer and you could find values for this based on a lot of data points. I'm just going to go through an exercise of using two data points. I have two parameters I want to I need values for, and so I'm going to make have two ideas on how to fit them. The first I'll say is that there's historical production prior to the drilling that starts for the particular situation I'm looking at. I'll say has a start time. Okay, I'm going to call that TS. That's, I know when it started. Right, and then I assume that I know the size of the reserves, which I'll just call 1 for this case. Alright, prior to TS, I could say there's historical production. It's out in the tail, and I would say that, use a rule of thumb, that at 5 time constants in the exponential is essentially at its asymptotic value. So I'll just fit it with -5 here. So that gives me one equation. Then I will take one data point. I'll say that at some time d, which is greater than the start time, I know the fraction of the reserve that's been produced. I'll call that d. That gives me two equations. I'm trying to fit two unknowns, this b and this ts, and the tm here. Ts I know. With some algebra, you can solve for b and for the Tm, which is going to be the maximum rate of production here based on that data point. So here is going to be my model that I'm going to use. This is a function that I'm going to use for this model, and I have two scaling parameters that I can put in for different situations. And now I'll do a numerical model just to show you that this works. So let's say production starts in 2001, so that's my start time. I know that 25% of the reserve has been produced by the year 2005, so TD is 2005 and D is 1/4. I put those back in the equations on the previous slide, and I come back up with values for B and for TM, and now I'm just going to plot the curves. And here's my prediction, and it looks just like a Hubbert model, right? Here was the one data point. Here was the start time, and I was able to fit a value to that saying it was essentially 0 but not exactly 0 at that point. The model predicts a peak around 2006, and at this point, 2011, it's essentially depleted. I used the logistics function for Q of T, which is the production, the amount produced, and took the derivative, which is easy to take with the logistics function, for the rate of production. So basically what I was trying to say in this lecture is that is to stress a difference between the assumptions made in a model and the mathematics itself. Usually, but not always, the mathematics is done correctly. The assumptions may or may not be valid initially, and they may not hold in the future. So the validity of the model does not rest on the mathematics, it rests on the assumptions. And that's that's an important point. Okay. The idea of keeping things simple is crucial, and it's just a really good policy, because the more assumptions you make, the more detail you put into a model, the more error you introduce. And then we went through the Hubbert Peak Model, which is very famous, and you can see in there how these principles were put to use to develop a very, very simple model. We then went on to play with the mathematics of it. And the mathematics part of it was just essentially playing. The real model was developed previously with the assumptions and with those first curves that were drawn.